was not expecting you to say that.
So analog signal in, we do a sample and hold first, and then this goes to the star block. 1, 2, 3, 4 bits, for example, and that goes to a DAC and being fed back to the inverting terminal. But you don't have to draw this diagram in the for the quiz. So the only thing you need to finish is just the state diagrams, right? So remember the star code register and sequencer will give you an initial state to be 1000 first, and that one is gonna be 5 volts exactly, right? So this is VDAC, and this is a VIN. Okay, and it compares, goes through the comparator. If V is larger, then you are getting a 1. If V is smaller, you're getting a 0, right? For 5 volts, and you know that your VIN is 6.2 volts. So definitely VIN is larger than VDAC. And you need to know that the 5 volts is coming from the VDAC, okay? Because this code is being provided by the SAR, right? So you got 1 zeros, and the DAC is going to give you a 5 volts to the inverting terminal, right? So that's why this voltage is VDAC, okay? VDAC. So V is larger, so we're getting a 1. In that case, it's plugging a 1 in front of it. Okay, remember how we did all the process? Just keep doing that, compare, and keep doing that. Eventually, you get a final state. So I posted the solution to Canvas already. If you still have questions regarding problem like this, definitely there will be one of the problem will be put in the midterm exam. So definitely you need to study this a little bit. Okay.
Is it just gonna basically be like a bunch of quizzes put together with different stuff?
Yeah, everything from the homework assignments or quizzes. Think about what we have learned from the beginning of the semester. The first week we did all the DACs, right? All the DACs calculations, Stevenin superposition, and then we did. I'm gonna do a review on Friday, really quick. Spice code, definitely I'm gonna put a spice code problem over there to let you write up the spice code. The pulse function, what are the arguments in the pulse function? Right, with the unwell resistors, the square sheet resistance, do you remember that? 800 ohms per square, right? And the layers, the cross-sectional views, let you draw that view based on the layout, the top view, and some descriptions of the pin junctions and body effects and stick diagrams, AOI logic, right? AOI logic. These are all the layout circuits, flip-flop operations being covered by the handout I just gave to you today, and also the lecture notes from here, right? So the flip-flops. All right, that's it. Haven't covered too much, but hopefully you learned something since the beginning of the semester. Something, right? Not a lot, but something.
Will you have a topics posted or a review?
Yeah, we'll do a review on Friday.
Okay, like a review sheet or
Study guide, like
Yes.
the Mac controller. Yes, I will do that.
okay.
Yeah.
Thanks.
Yeah. All right. Any question on anything by far before we move forward? So finish up our flip-flop stuff today, and cover a little bit about the voltage doublers and then charge pumps, because it's being used for the ADC. So look at the D flip-flop, the TI DFF. So we talked about the D flip-flops triggering at the rising edge, but we did a set whenever we do active 0, it's a setting, and also we didn't. Also, there's a resetting, but we didn't cover that on Monday. So that's why we are doing this right now. So we have latches. Clock going to here. That's a NAND gate as well. Output, Q naught, D. Remember that when we have, so we already verified that this is a rising edge trigger DFF flop, right? And if we put a reset here, it's active 0. It's being fed into here and here. If you're putting here, this is definitely being put into a 1 because 0 will kill this NAND gate and put a 1 here, right? And this one here as well. 1 and 1 NAND clock is clock not. Okay, and 1 will be putting here. And remember this line, okay? Don't forget this line, okay? So clock not is being sent to the another input of the NAND gate. So clock not NAND clock will be definitely 1, right? Because clock not and clock will be 0 and being inverted will be 1. So this will be 1 as well. This is 1 as well. And this was 1 here, 1 1. Being NAND, you got a 0. 0 comes back here, 0 NAND everything is 1, so 1 comes out 0 1 0 1, stable, okay? Eventually. Stable. So it's resetting it, definitely, no problem. I can reset it by doing this. So now let's look at setting. So how can we set it? Oh, sorry, this is setting actually.
Yeah.
Jesus Christ. Yeah, setting. Okay, because this is 1. This is setting. For resetting, here. Don't forget this line. And we already know that we have a set here. It's being sent to here and here. Now let's add a reset. Reset needs to be added here, here, and here. See if that works. If you put a 0 here, it's also active 0, okay, active 0. So put a 0, it will reset it. If you put a 0 here, this becomes 1 immediately, no problem. Okay, and since we are resetting it, do we want to set it at the same time or no? No, so this is 1, right? This is 1. So 0 here, this is getting killed, got a 1 for sure. Right, this guy. And same for this guy, 1, 1, right? So got a 1 here, being fed back. This is 1, this is 1. So we know this is a 1, so this is being fed back to this guy, it's 1. 1 1 1 NAND, you got a 0 here. 0 here. This is clock. Is it affecting this pin here? if you got a clock 0 1, no, clock 0 0 0 0 clock, it's not changing because 0 and then anything is still 1, right? So it's not changing it. So clock 1 1, what is this guy?
It'd be a 1. No, it'd be a 0.
1 clock 1. What is this?
It'd be 0.
Wait.
1.
No, 1 clock 1, none. Clock not, right? Clock not. We know this is the 1 for sure. 1 comes to here, and this is 0. Because it's 1 1 1. This is 0. 0 comes to here. 1. Doesn't matter what that is, right? Clock not or something else doesn't really matter. So 0 will just kill this NAND gate. So 1 0 1 0 is stable, right? So Q is being reset in this case. Q is being reset. So now we know that it's a pretty good circuit design, very smart, and it's D flip-flop, rising edge trigger, set and reset, perfect. So we are. You can see this structure is being used in a lot of ADC designs, the D flip-flop, or a lot of other digital circuit designs. It's very important schematic to learn. So that's why we have this in this class. It's not on the textbook, but it's important to know. Okay, we are talking about D flip-flops, but I've never seen a functioning D flip-flop in your real life. So this is the one you can use. It's gonna work. Okay. So the one I gave to you is another D flip-flop circuit. It definitely will take a less footprint. It's the IC version. Usually, if you want to save some space, this is the one you want to use. And I'm asking you guys to write a description of how this is going to work on the paper and turn it back to me. I'll give you some credit on it. Let's say 10 points. Forgot to put number of points on that, but I said 10 points. Okay, 10 points. How that works? Take a look. It's a D flip-flop. It's a D flip-flop.
Where's the set?
Where's the set and reset? So here's the reset. Set is not being included, but you can definitely. So these ones. So if you have an arrow on the top, that's PMOS. Okay. If you have an arrow at the bottom, that's the NMOS. Just to let you guys know. So these are PMOSes, and the rest are NMOSes. Yeah, it's not trying to give you a hard time. It's just let you guys pay attention to the class when I'm talking about this.
So,
It's been pretty effective.
well, I guess that's my question.
Yeah.
If it doesn't have a set, then how is it?
Yeah, you can add a set. See?
Oh.
So the thing is, you see this is the final stage inverter, right?
Yeah.
So when you reset it's active 0, you put 0 here, this point is being put up, right? Being put up.
Yeah.
So you're getting a 1 here, 1 getting inverted, getting a 0. So that's how you're resetting it, right? If you're setting it, you just add an NMOS at the bottom.
Oh, you just simplified it and.
Yeah, just add an NMOS at the bottom.
We'd understood that.
Right? So that's set. But you are not setting and resetting at the same time. Why? But if you do it, what's going to happen? Setting and resetting, you want to turn on the PMOS and NMOS at the same time?
Short to ground.
You are shorting the VDD to ground. It's drawing a lot of current from VDD to ground. It's not doing anything actually. It's competing. So if you turn both off, doesn't matter. This node is just this node. It's just staying there, doing whatever the D flip-flop is doing. And also another quick note here, okay? Because when you are setting and resetting the circuit, there's a risk actually compared to the TI one. I actually prefer the TI one instead of this one. Because you can see that if I have, for example, I don't have this setting here, just reset, okay, just reset. And when you are setting or resetting a DFF flop, it should set or reset whenever it wants it to set or reset, right? It shouldn't depend on the clock cycle or the D or anything else. So if you are resetting, but just during that time frame, clock is on, this is on, what's gonna happen?
Shorted.
Yeah, it's actually shorting this guy to ground. So in that case, what can I do? I mean, but this is still resetting it. If you still want to reset it, I mean, there will be some channel resistance. It won't really shorting it, but it's probably more about competing, right? So one is pulling down the ground, one is pulling up to VD, which is stronger, right?
Yeah.
So, but you still want to reset it, right? So what should you do?
Well, you need another one.
Mm-hmm.
If you want to guarantee that it's reset, you want to make sure that it's grounded, right?
Yeah.
So you probably have another MS. Like
So yeah, that's all of the resetting circuit here. It's just a PMOS, one PMOS, right?
Yeah.
Oh, it's a resetting. Sorry, I'm resetting. So if you're resetting it, but not you want to make it independent to all the cycles over here, right? So if these are on, it's gonna pulling this down, but you want to pull this up, right? So it just makes this super strong. Okay, just make a super fat, big and fat PMOS on the top, so you can guarantee that this will be put up. Okay. The thing is, this is only competing with these NMOSes, and because these are all just the digital transistors, and these are not super big, I can guarantee you. So if you make this huge, definitely this will be a very strong pull up. And same for the NMOS, right? So this NMOS is probably competing with this PMOS at the moment, right? So it just makes this NMOS super big, super wide. So whenever it's pulling it down, it's able to pull it down. So you are not setting a resistance at the same time because both are strong, and that will be a pretty weird situation. But you are not turning on both at the same time anyway. So that's about setting and resetting. Pretty straightforward compared to the previous one, right? It's just basically pulling up and pulling down. But if you look at the D flip-flop operation, it's a rising edge triggered, and D. We are looking at the D, right? So see if D can be sent to kill. That's what you have to put on the paper as a description of the operation of this D flip-flop. Okay, now let's get started. So if you look at D here and look at this structure, so what this looks like, even though there's a little tiny channel in the middle. So what this looks like, PMOS on top and most at the bottom, the gate are shorted. What is this? Inverter. It's the inverter, right? It's a clocked inverter. You got one clock in the middle control the channel, right? So sometimes you can turn on and off. And you can see this output is shorted to the lower side instead of the higher side, which will determine some properties of the operation. But now let's just look at it. Every time we analyze the operation of the DFF flop, we start with 0, right? So right before the rising edge. So whenever it's 0, what's going to happen? If you look at the clock, it's being shorted to these terminals, right? What you can see as an experienced, seasoned electrical engineer. It's different, right? But I mean, if you don't know it, you look at the circuit, it's just a bunch of transistors, right? But if you are seasoned, you'll tell, oh, this guy is different. All right.
Oh yeah, it'll pull up.
Oh, this is different. Pull up, yes. So whenever clock 0, what is this guy doing?
It's pulling up.
It's pulling up, or you can say, hey, there's a channel, it's dumping charges to this node. That's what's happening. So this PMOS is special, right?
Yeah.
Just pulling this up to what? VDD, right? VDD. So there will be some charges stored there. Okay, stored there. And you are talking about why is this point is not being put down to the ground? Because this is NMOS, right? NMOS, when clock 0, NMOS is off.
Yeah.
So definitely it's disconnected from ground. So it won't be So the charge being stored here won't be discharged. And on the other side, there will be shorted to gates. So not the channel, so it won't be discharged. So it's going to be stored over here. So what is able to store charges? What's the component can store charges? Capacitors, but there's no capacitor. How do you store charge? How do you store the charges?
It becomes a capacitor. Like a voltage.
Remember the gate oxide? All the CMOS transistors have the gate and oxide in the middle, and then the channel, right? So all these are forming capacitors. These are pretty small value capacitors, like hundreds of femtofarads. So all these are parasitic capacitors, and a lot of times it's causing time delays. But now it's just like a charge storage devices. So there will be some charges stored in here. Okay, so when clock 0, it will dump charges to this point and being stored over there for sure. Okay, it's going to be a floating. So a professional term here is it's a floating one, right? It's a floating one. It's not a solid. No, if you keep this PMOS on, it will be a solid one because this is a power source. If you connect the power source to the outlet on the wall, it's being backed up by the power plant of the city, right? So it's a super solid power supply. So it's actually not a floating power source. If you turn this on at the moment and then you shut it off, and this voltage, will this voltage change or not? It's basically like you have a bucket over there, right? You dump water from the top. You dump water and fill it up, and then you shut it off. Are you losing the water from the bucket? No, it stores the charges, right? And at that moment, it's called a floating one. It's a floating VDD instead of a solid VDD. The reason for that is if you discharge from that bucket, it's a finite amount of charges. It's not like a power plant backed power source, right? So it's a finite amount of charges, but it's still holding a VDD as a voltage, but it's just finite amount of charges over there. You can discharge it, it will decrease, right? Decrease to 0 eventually. Okay, so that's a model, kind of model or thinking you need to know, keep in your mind. So at the very beginning, clock was 0. So if clock 0, the PMOS is on, right? PMOS is on. So if PMOS is on, you can treat this guy as a wire. And this terminal is what is the output of the inverter. So if this guy is an inverter, right? It's an inverter, and if clock 0, this is the wire, and this node is exactly what?
It's D, right?
Hmm?
D
Yeah, D naught. So that's how you sample it. So that's how the data get into the process, right? So the data will be sampled in there. And now before we analyze the following circuits, the data is in, so we know D is in. But eventually we know it's a D flip-flop, so D will reach here, but now D naught is here now, at least, right? D naught is here. What's next?
Well, then it goes into NMOS, right? So
Yeah, so the thing is, because this is being put up, right? It's being put up. During 0 is being put up. And what's happening for this guy? During 0.
off.
Even though, yeah, it's off, right? If this is off, this is being put up, and that's a PMOS. It's on or not, on or off. If this is being put up during 0, it's being put up, right? This is being put up. Is this on or off?
it's off.
Off, right? So what is this point? No.
Oh,
Is this being put up?
if you pull,
Is this being put up if this is off?
No.
No. If this is off during 0, is this being put down?
yeah,
No. So what is this guy doing here?
nothing. Well, is this
Nothing. It should be something, right? Memory. Yeah, it's a memory. Yeah, it's,
that's where the memory
yeah, it's using all the charges of the gates, right? All the parasitic capacitors is holding a charge here. It's a floating charge. It's a floating charge, but it's still a charge, right? So that charge, and there's no control after that because it's just an inverter. It's not being clocked. There's no control. So that charge, that memory, that data, whatever was stored over there will stay, right? So it's a memory. So that will be inverted as a to send to kill. So it's not changing. So at least right now we know that during when clock 0 it's a memory. It's not changing anything. Okay, so by far we know when clock 0 this is D naught, right? And also this is the memory here. So now it reaches the rising edge. Reaches the rising edge. So the rising edge will do what? Will turn off this guy. Okay, will turn off this guy. But will that affect this guy or not? Wait. Will it? Is this going to affect D naught or this point? Let's label this as A. This point as B. This node as B. It's A, B, C. A, B, C. Okay. Is node A going to be changed? Why or why not? If I have a rising edge here, the rising edge is going to shut this off, right?
This would be put on the
Why?
right? Because there's a mouse there.
Almost there, but almost is not being clocked. The clock's not changing, right? We're assuming D is not changing. What's going to happen for D naught?
Just gonna stay there.
It's going to stay. It's a very similar thing like what I just described, right? You have a pipe on the top of the bucket, you just shut it off. It's not changing, still D naught. What about this one? It's NMOS, right? What about this one? It's a PMOS. So this will be off, and this will be turned on. Okay? If this is being turned on, now let's see. If D naught is 0, what's going to happen? I mean the whole thing, not D. I mean D naught, the whole thing. If the gate input here is 0, right? If here is 0, what is happening to this guy? Off. Almost off, right? If this guy is off, even though you turn this on, what's going to happen to node B?
It's
Hmm?
it would be 0, right?
Hmm? This is 0, right? If this is 0, this is off.
And the clock is
There's no disconnected from the bottom. Even though this is on, it's not pulling this down to ground, right? Stays at what? Hmm? VD. Why? Because the previously this was 0, so it was put up. Okay. So now the conclusion is, if I have a 0 here, and this will stay at 1. Okay. If I have a 1, for example, D naught here, now it's not 0 anymore. It's a 1. It's a 1. What's going to happen? If this guy's a 1, what's going to happen?
it's going to activate the mouse.
Yeah, this will be on, right? And is this on or off?
That'll be on.
This is on because the rising edge is on, right? Both are on. What's going to happen to node B?
That becomes 0.
It's being put down to 0. So if I have a 1, you got a 0. If I got a 0, I got a 1, right? So what is this B? Node B. D. So at the rising edge, this little D naught will be sent to node B as a D. And now this structure is very similar, right? Very familiar with you guys. That's the NMOS at the rising edge. Definitely there will be some kind of delay, but the rising edge, after the rising edge is the logic 1. Okay, so the rising edge will have this D reach here, D reach here, and then rising edge will turn on this guy, and this is another clocked inverter. However, the output is shorted to the drain of the PMOS instead of here, like this guy. So it's going to be something different here. But you can see D is here, rising edge, this will be on, right? Rising edge, this will be on, right? So NMOS, what's going to happen? That's an inverter. So what's this point? D bar. and now it's out of control, right? Now it's out of control eventually. So what is Q at the rising edge? What is Q?
Q is D.
Right? It's an inverter, right?
Yeah,
D. So Q is D. So now we know that this is rising edge D flip-flop. So the key point of the analysis of this circuit is you need to know that this guy, this point, was previously charged to VDD during clock 0. Okay? That's critical. Okay? Because that will either remain at that VDD, that's how the VDD comes, as the VDD comes to this point, either remains at VDD or it's being put down to ground whenever the clock is high at the rising edge. That's a critical point. So if you know that, the following ones are pretty simple because this is another clocked inverter and this is out of control, right? It's out of control. Okay. So now, if it moves, it remains at 1, and this guy changes from D to D naught, what's going to happen? What's going to happen? We're going to verify this guy is the rising edge trigger D flip-flop. So it sends D to Q at the rising edge, and whenever it stays at 1, it shouldn't, if the D changes, it shouldn't change Q, right? So that's the whole point. So it's not a level trigger, it's an edge trigger. It's an edge trigger, not a level trigger. So now clock is 1. Clock is 1. And D changed from D to D bar. What's going to happen to node A? Node A, what node A is going to do here? Node A. Clock is still on, right? So the PMOS is still off. This PMOS is still off. So if D changes from D to D bar for this guy, for this point, because this point is shorted to the lower node of the clocked inverter, right? It's over here. And this is disconnected. So this point is disconnected from the voltage source. If you change D to D bar, what's going to happen to A?
It'll stay. Or it'll.
Depending on D, right?
Yeah. It depends on whether that NMOS is on or off.
Yeah, so this guy is shorted to the gate of the NMOS. So the NMOS, depending on D's value, NMOS could be on, right? If during the change, NMOS could be on. It could remain off or could be on. So what's going to happen to this point is, this point could be either 0. If it was 0, it will stay at 0. Or it will be put down to 0.
It should.
Wait, is that the case? So let's just give examples, right? So if D is 0, okay, D is 0 originally. So D bar is 1, right? D bar is 1. And now it changes from this to 1. Okay? So this guy will be on. And this one will be discharged to ground. And this one becomes 0. Okay? If you had 1, 0 for D and D bar, if this one changes from 1 to 0, this will remain unchanged because it's disconnected from VDD. There's no way you can charge it up. It will either be discharged or remain at 0. So if you had a 1, it will be discharged to 0. If you had a 0, it will remain at 0. So the conclusion is this guy will be 0. It will be 0 eventually. Okay, it will be 0 whenever this changes. No matter what, if this was a 1, it will be discharged to 0. If this was 0, it will remain at 0. So what's going to happen to the following nodes, though? You can see This so eventually the conclusion is that this NMOS will be turned off. Will be turned off. And what about this guy? When clock is 1, this PMOS is off as well, and this is off. So it's being disconnected from both sides, and this guy will do what? Will remain the same. Will be held by all these parasitic capacitors. It will hold at D. Okay? If this guy remains at D, even though this is on, it's not a clocked inverter, it's a static inverter right now. It's D, D naught, and then D. It's not changing. So for this part analysis, the critical point is you need to know that this point is either remain at 0 or being put down to 0. So that's a critical point for analysis for this part.
But Q doesn't actually change though, right?
Q doesn't change because D doesn't change. D is not changing. D naught is being inverted twice. Right? So D is still D here. Alright. Questions on this? Just describe it, you know, based on whatever you learned your English from the last 18 years.
Yes. Okay, I guess the fourth scenario would be like falling edge. Or like,
Oh, falling edge is 0. 0 is not changing anything.
yeah.
Right? Remember that 0 is giving a memory here.
Okay.
So falling edge is 0, right? So whenever clock 0, this is a memory. We already did it. I did it because falling edge, this is 0, disconnected, and this guy. Wait, whenever clock 0, high. You just don't know because all these are off, right? So that's why this remain unchanged because all these are disconnected. Because this is high, right? So you go high here, this is off. And this is on, but the thing is this is off. So this is not changing.
Well, yeah, and I guess if you had. So what are you asking for again?
Oh, describe how this works. You can label node A, B, C, right? Label node A, B, C. And start from when clock is 0. When clock 0, these are off. Oh, when clock 0, this is on, right? This is on, so this is off. And this is disconnected. So your node C will be memory. And at the rising edge, it does the following, right? It does the following. So describe it and submit it on Friday. You don't have to submit today. So watch the video and study this and turn it on Friday. It's a little bit unrealistic for you guys to get it in today right now. So